So thank you very much for the invitation to talk today to you, and also for the kind introduction, Benoit, with regards to the spelling or to how to pronounce Dechema. It's Dechema in German, if you wanted to know that. And so the work I will be talking about today has actually been performed over the last, let's say, 30 years at this institute in Frankfurt. It's in downtown Frankfurt, as you can see on this little photograph at the bottom of the slide. Surrounded by the skyscrapers, so we are among the smallest buildings in this area. And so much of the work that I will be talking about today dates already back quite some time when I started at this institute in 1978, and I'm still associated with this institute. So even today I have a couple of projects with people going on there. And in those days, the idea came up not to investigate only the chemical aspects of high temperature corrosion, but also to look at what's going on if mechanical aspects come into play. Because this was mainly from the gas turbine industries in those days, people had seen that damage cases usually are based on the interaction of mechanical loads and high temperature corrosion, and not just of high temperature corrosion alone. So what's actually happening to these materials can quite nicely be described by this little cartoon. So the materials have to suffer quite a hard life in their service. Like you can see it with this little guy sitting in this kettle on the fire here. And they have to survive. So they must be very strong. And of course, you must know what's being done to these materials and how they react on their loads and on their corrosion attack in real life. So I think, first of all, we need to talk about what is specific about this interaction between high temperature corrosion and mechanical loads at the same time, affecting the life of these materials. Now, I don't know how deep you are in high temperature corrosion, but usually, and this is pretty much the same as in electrolytic corrosion, these materials, they survive as soon as they form a protective layer, a passive layer, kind of a passive layer on the surface. And I think we've heard it already in two talks before, at least in the first one, where an alumina layer was addressed underneath the TBC. And this alumina layer is such a protective layer which keeps high temperature corrosive attack away from the substrate material. And such layers are the key to the performance under corrosive conditions at high temperatures. So we will have to look quite closely at such protective scales, even from a mechanical point of view later. You can see what mechanical loads can do to these passive layers. This is a very simple case with a very simple oxide. Let's call it a model oxide, which is nickel oxide on nickel. And you see what can happen if stresses damage these oxide scales. Complete flakes can break out of the surface of the scale and can fall off, so that the material, the metallic material, is again exposed to the corrosive environment. And that can be the beginning of the end of life, and that corrosion or corrosive attack, increased corrosive attack, can start with such weak points of the surface. And not only, let's say, on a kind of a macroscopic or pseudo-macroscopic failure way as here, it can also happen in a submicroscopic scale, which means you need a TEM in such a case, for instance, to see that even cracks, micro cracks, can occur between these grains of an oxide scale. So as this image is shown here, and they can be so the aggressive environment can permeate through the scale even via these micro cracks. Also, you have the feeling that this is a completely undamaged scale. So sometimes it can be enough to increase already corrosive attack that you have such micro cracks in the oxide scale. And a very important feature of such scales is that a good scale usually has capabilities of crack healing, which is shown here. So there was a crack before, and then you can see that if there's good conditions, that the crack can heal at the bottom, where originally the material was exposed to the corrosive environment. Now, by forming new protective oxide between the two crack faces here, this crack can be closed again, and then protection can be restored. If in some cases, if the depletion of the subsurface zone of the by the metal of the metal that is needed to perform or to make the protective healing. So if the depletion has gone too far and not enough of this alloying compound is existing anymore, then it can happen that the oxidation mechanism can switch from protective to non-protective at such a crack. That's something we can see here, and that's called the breakaway oxidation. So here, this was the thin layer, oxide layer in the cross section, and then after breakaway, such a thick oxide can be formed here, which means that no longer the same protective situation exists as it has been here. And another interesting slide is actually also this one here. You can see this is an oxide scale in the cross section here, and where there are the cracks here, then the subsurface attack starts, and so the damage starts, which is a good proof that we need protection by such an oxide scale, in that it must be defect-free, non-damaged, must have a good protective effect against the environment, which would be out here. So when we look at the next step after actually what has happened here with the crack formation in the oxide scale, which means what's happening next after these cracks, it can happen that oxidation or corrosion can lead to crack initiation from the surface. And this is an example. We have hundreds of such cracks starting at grain boundaries, and these cracks have been formed due to oxidation along the grain boundaries and tensile stresses or tensile strains in a creep test here. So you can see that all these oxidized grain boundaries close to the surface, they were evidently very brittle under such conditions, and that means even in the creep test at 950 degrees C, where the metallic material would be quite ductile, this would be enough that by grain boundary embrittlement, these grain boundaries can crack or start cracking at high temperatures. Now, there's a couple of different stages that can happen and finally end up in failure of the material. And this was at the beginning of the 80s, and that's why you see that it's quite a historic slide here. It's not that sharp as it should be here. That we introduced the corrosion deformation interaction diagram, which was based on the two parameters, strain rate, which is on the abscissor, and strain, which is on the ordinate here. And you can see there's a couple of different stages in the life of the material, depending on the strain rate, which is active. And I would focus now on this range, which is below a critical strain rate, which is needed for crack healing, which I would call the technical range, because usually under technical application, we have relatively slow strain rates, and we usually stay in the area left of this line, which divides the two parts where the strain rate is slow enough for crack healing and where the strain rate is too high for crack healing. And now, of course, the first stage is that the protective layer may crack, protective scale, which is the stage number 1. And which means stage number 1 is we move from the still intact scale to a situation where the first cracks can be formed. As here, for instance, you can see this here. So this is a critical strain. Once this strain is reached, cracking occurs. And if we are below this critical strain rate for crack healing, then the protective effect can be restored. As we've seen this before in one of the slides, and that this crack, which usually goes through the whole scale here, which is on this side, you can see this crack which goes through the whole scale. It can heal by oxidation at the bottom of this crack, so it's refilled again, and it can be completely closed again. You can see some features here which remind you of very short cracks, but which are actually healed cracks. And so in this case, the protective effect is completely being restored by the healing process. Again, you need to be below a certain critical strain rate, because otherwise the growth processes of the oxide would be too slow to close this crack again. And now, after a while, then by continuing cracking and healing, subsurface metal, the protective subsurface metal like chromium or aluminum is being consumed, then the depletion can go as far as that no more protective oxide can be formed and no healing can take place anymore. And then we end up in a situation as given here in 3', so that no more protective healing can take place. And once the internal oxidation along grain boundaries starts, then we can end up in a situation where corrosion-induced subsurface crack initiation can start, as we've seen it in the slide before. And this may move on to a stage where then corrosion-supported or corrosion-assisted crack growth can take place. So this is actually a diagram for orientation first, but it is worthwhile also to look at quantitative data for filling this diagram with the data. And in my presentation, I would like to focus actually on two situations. One is the stage 1 situation. What is the limits of the stage 1 situation, which means when does scale failure occur, at what strain? Because that is the very first step leading to component failure after a while, after going through all these stages up to the one where the corrosion-assisted crack growth may take place. And that is the last stage. So that's the other point which I would like to address today quite briefly, which means the very beginning and the very end of life under the effect of combined stresses and corrosion at high temperatures. So let's start with the first point, which is can we measure such strains, such failure strains of the protective oxide scales? Of course we can, and I put together here a list of references. If you find the time and if you're interested, you can have a look at all these papers and see what has been written there. So it's quite old papers, partially starting in 1997, for instance, going up to 2017, which is one of our last papers in this area. Now, the first method that we used in the old days was that we just took a tensile test specimen, like here, in a tensile testing machine, and then we spot welded a platinum wire to the specimen and had some, I would call it microphone, an acoustic emission sensor attached to this platinum wire. And the whole thing could be done in a furnace, so we could measure acoustic emission even at high temperatures. And since the substrate itself, the metal substrate itself, is quite ductile, this leads to a very different type of acoustic information or acoustic signals than the brittle oxide, which is formed on this metal by oxidation. So acoustic emission is always a good tool if you have brittle materials, because then you get quite strong signals in this case. Such a combination allows to measure the failure of the brittle surface oxide, and you can distinguish this quite well from the ground noise. I would call it the ground noise of ductile deformation of the metal. And so, oops, the wrong one. In those days, we measured the critical strains for a couple of different oxide scales, for instance, alumina or titania, nickel oxide, chromia, and alumina. And there's one common thing with all these materials, or with all these oxide scales, that even at elevated temperatures, 800, 900, and 1,000 degrees C or more, they behave like you would expect it from ceramics. They are brittle. And when you look at the critical strains, they are clearly below 1% of strain. In most cases, it's between 0.2 and 0.6% strain. So this is not a lot. It's quite low, which underlines the importance of the capability of such a scale for healing. If you would not have healing of such oxide scales, you would have a dramatic corrosive attack probably very soon in lifetime of these materials, since such slow strains can always be reached under operation. Now, later on, we developed another technology or another technique for measuring the critical strains, and this is the 4-point bending test. The 4-point bending test is more accurate. You have a better, more accurate situation concerning the stress situation in these oxide scales on the surface of such a 4-point bending specimen. And you can also locate the events on the surface of the specimen. If you have two sensors, you can find out where is the signal coming from. Is it coming from here, or from here? Especially with modern electronic equipment, it's very easily possible, as you see down here, to locate the position of the signal. And of course, you can also make an analysis of the type of the signal, of the energy, of all the information that is contained in the acoustic signal in this test. And you can do it, of course, if you have, again, platinum waveguides here. You can do it like shown here with a furnace. So you have the 4-point bending equipment in here. And you'll see these are the platinum waveguides coming out here on either side. And you have the amplifiers, the preamplifiers here, and the whole thing goes to some, well, quite sophisticated electronic equipment now, where you can do some very detailed signal analysis nowadays. And this shows a schematic of the information that you usually would like to get. That is that with this is compressive strain here, of course, usually you can do it also under tensile strain. So after a while, the energy or the number, in this case, it's the number of acoustic emission hits, starts to increase strongly. And this is usually the case when you have large-scale cracking going on in such an oxide scale. And by locating the signals, you can also find out where it actually takes place, and you can correlate this also with the local strain on this 4-point bending bar. So usually in this case, this example shows two failure steps. One is the delamination of the oxide. The other one is the through cracking under compressive stress. You see two such maxima, which means one effect is starting at a relatively low strain here, and the other one comes later. So what we want to do by these experiments, we want to quantify the critical strain that leads to cracking. And it's not always that easy as it was shown in that slide. It can sometimes happen that the acoustic signals from the oxide are superimposed by signals from the substrate. And this is something which you can see here for the example of cobalt oxide. And in this case, it's necessary to do some more detailed analysis of the signal. And you can see if you do rise time analysis of the signals, then you can separate the two effects here. And by separating these effects, then you can you can measure the critical strain of the oxide, can separate this effect from the other superimposed effects from the plastic deformation of the substrate. Oops, again, the wrong one. And this would then lead to results as shown here. For instance, indeed, now we can see, and this is again for tensile strain now, you can see at the beginning not much is happening, and then suddenly the acoustic emission activity starts to increase significantly, and by that you can determine a critical strain for the failure of these oxides. Now, what we actually want to have in the end is an information about the mechanical properties of these surface oxides, and this information can be obtained ideally by establishing these diagrams, these scale failure diagrams, where the critical strain to failure is related to the defect size in these oxides, to the micro defect size. This is actually a fracture mechanics approach, where strains are related to defect sizes in materials. And the relation between these two parameters is actually given by a mechanical property parameter of the oxide, which is eta. So with the eta parameter, you can see this eta can be different for the different types of failure. These eta values have been determined here from experimental values and have also been obtained in model calculations. So there's both ways possible. And this is what we in the end want to have. So why do we want to have this eta parameter? And this is the equation which is behind this eta parameter. Critical strain is related to the size of the potential micro defects in the oxides, related via a constant eta. And this can be compared actually, for those who are familiar with high temperature oxidation, with the Kp value, which is the oxidation rate constant. So this is a typical materials parameter for the amount of oxidation that can take place at high temperatures. And this is a typical parameter describing the mechanical properties of the oxide scale formed under such conditions. And to illustrate it further, a high eta actually means we have a high fracture toughness or low stiffness of the material. And if the eta value is low, it's the opposite. So by the eta value, you can characterize the mechanical properties of these oxides that have been formed on the surface. And there's also some more information that can be taken out from this eta value, which can be associated with different types of behavior. One of, for instance, is the influence of environment on the mechanical properties. So it can be that actually an eta value that was high in one environment may become low in another environment. Or what can also happen that the eta value actually remains constant, but this is now what we see here. It can happen that the environment leads to differences in the micro defect formation, so that one environment has lower defect sizes than, for instance, the other environment. So again, things may happen that, for instance, the critical strain drops because the defect sizes increase due to a change in the environment here. So how can we determine the zeta value? Well, it's quite obvious. What we need, that's what we get from the acoustic emission tests. We need the critical strains, and we need the defect sizes in these oxides. This is here given as an example. It's something that we can get from metallography or from SEM, for instance. This is a binarized image by the computer, binarized by the computer, and then you can see these black spots here. Those are the defects in this case. This was a nickel oxide with a lot of defects, with large defects, for instance. There it was easy to determine the defect size, but this is the way actually to get to the value of the C, of the critical, of the defect size. So we need these two values, and then we can determine such diagrams as given here. This is a type 1 diagram for titanium oxide. And you can see that indeed a change in the eta value takes place if we move from a dry to wet environment. So you can say that this is the dry, this is the wet environment. that the oxide becomes kind of more ductile in the wet environment. And we can, of course, also see an example for the other type of behavior where wet and dry actually fall on the same curve. So the eta values are quite the same or quite similar or quite close to each other. And evidently, in this case, it's more the defect sizes that are affected by change in the environment. And for instance, here for the other oxides, for the iron oxides, we can see that it's becoming much more complex. Even probably the two effects are mixed with each other in this case here. You see in part of the diagram, oops, here we are. This line is above this line, and then if we go further with the defect size, then it changes. So it can even happen that the change between type 1 to type 2 behavior is possible, or that even in one type of behavior a change occurs, as it's given here. So these are the values that we want to have with regards to the behavior of oxide scales for the description of the mechanical properties. And these values allow us to do a very conservative assessment at first to find out when do we have to expect the first mechanical failure of these protective oxide scales, which does not automatically mean, as I said, that this is already the very beginning of corrosive attack underneath the oxide scale, because healing can prevent such attack. But it is, of course, already the first time in life that we have a critical situation where a material shows some Achilles heel, I would say. So, and then let's switch to the end of life, which means to the growth, to the corrosion-induced or corrosion-assisted crack growth in a material under high temperature corrosion conditions. And again, there's a couple of papers that I would recommend to read. Also, these papers go back until the first one in 1989. And so this is also the reason why this photograph on the right side is not the best one. This is a pretty old one, which shows the equipment that we built up for this case, which is a tensile testing machine. And there we have ceramic pull rods, ceramic pull rods here, and in the middle there's a CT, a compact tension specimen. So I apologize, this is in German, but I can explain it to you. So we have a furnace here, and we have an environmental chamber around it. We have the ceramic pull rods, and we have this specimen where we do the crack growth measurements here. And of course, the whole thing must be closed against environment, because we took in some cases, we took very aggressive environments in here and let them react with our specimen here. So you see there's a quartz tube around here. This is the specimen. What you can also see here is the wires for the measurement. So we did measurements by the so-called potential drop technique, which allows us to monitor the growth of the crack, the creep crack in the CT specimen, as it is shown here. So we have a modified compact tension specimen in this case. In some cases, we even had this modification here, which made it easier to weld the measurement wires to the specimen here. And so what we measure by the potential drop technique, this is shown here, is that we send some current through the specimen, which comes out on the other side again. And depending on the remaining cross-section here, after crack growth or during crack growth, then you get a signal, which you can measure here. And with this signal, if you calibrate this, you can measure the crack growth rate, even again at high temperatures in aggressive environments for such kind of specimen. The crack actually, so we have a starter crack here, and from this crack, this will grow further into the, no, actually it's the opposite. This is the starter crack, then the crack grows through this specimen, and this is what we monitor in our measurements. And now here, 2 examples of what will be coming out from these measurements. And you should actually ignore this part of the curve. This is due to the measurement technique. Interesting is actually this kind of, these lines here. And this is a plot where a fracture mechanics parameter, so it's the high temperature fracture mechanics parameter C star, which is being used for ductile, for creep ductile materials, where the crack growth rate is related to this C star value here, and then you get such a scatter band here. And in this case, the question was whether there's an influence of the oxidation on the crack growth rate here. So we had the inert environment compared to air, but you can see there's actually no difference. So the crack growth rate itself is not affected by the oxidation, but as we'd seen before, the crack initiation can be assisted by the formation of grain boundary oxides in the subsurface region. Now things can be quite different if we move to so-called creep brittle materials, which means materials that have a much higher strength, creep strength. And so again, we have the inert environment, which is here, and you see there's some materials which are quite sensitive to the environment with regards to creep crack growth. So especially this one here, the 716 or 718, shows a strong acceleration of the crack growth rate in the presence of oxygen. So, and in this case, since these are quite have a high creep strength, you can use the K parameter instead of the C star parameter as the fracture mechanics parameter. Now this was for air. You can do the same thing for much more aggressive environment, for instance, which in this case was 2% chlorine gas in air. And you see that the creep ductile materials again are much more tolerant to corrosive attack with regards to creep crack growth, but still, and those are the chlorine values, you have a little small acceleration here with regards to the creep crack growth. Those are the air values here. But as soon as you move to the more strong materials, the creep brittle materials, and this is the chlorine value here. So you can see there's at least 1 order of magnitude here, down here, in acceleration due to the presence of corrosion. So as a conclusion, one can say that the creep ductile materials actually are less prone to an acceleration in creep crack growth by the presence of high temperature corrosion than the creep brittle materials. So I think that takes me to the end, yeah. So as a brief summary, I showed you that the complex situation of high temperature corrosion under mechanical load can be described by such corrosion deformation interaction diagrams. And what I showed today, and this is also pretty much what you can probably find in the literature, is that the experimental investigations that have been done so far very much focus on the first and on the last stage in materials life under such conditions. We've seen that the scale failure in the stage 1 can be quantified by this eta-based scale failure diagram approach. What we need is metallographic cross sections for the defect sizes and acoustic emission results for the critical strains. And then for the final stage, for the crack growth leading to failure, we can measure the influence of high temperature corrosion by a high temperature fracture mechanics approach. And then we use the CT specimen under creep conditions and look at their interaction or how corrosion affects creep crack growth. Okay, so that takes me to the end, and thank you very much for your attention.